Yes, sir. The last theorem I got out. Means, can you re-explain that?
Last theorem means, okay, anyway, let me revise main results first of all. So, in the previous lecture, basically we discussed in some of the previous lectures, we discussed that if we have a linear function from a nonlinear space to another nonlinear space, then to check it is continuous, we need to only check that it is continuous at the origin. It is enough to check that. And then we discussed that whenever we have a linear function on a finite dimensional nonlinear space, then it is always a continuous function, right? So domain should be finite dimensional nonlinear space. If it is infinite dimensional nonlinear space, then we have discussed one example that this result is not true in general. Now we discussed this example of L2, and then we discuss some example of C00, that on C00 we can, yes, this is exactly that example of the second part. Okay. And then we discuss some examples to just discuss this theorem essentially, that whenever we have a function which is from R to R, that means from a nonlinear space to nonlinear space, if it is not linear, it is not continuous at zero. And whenever we take a linear function, it is always continuous at zero. That is the example. And okay, what next? So you are talking about this theorem.
No, no, no. At the last, you have told.
Okay. Okay. So this is a main theorem. We can say regarding the continuity of a function, continuity of a linear map. So remember that we are taking linear function here between two nonlinear spaces. So whenever we have a linear function from between two nonlinear spaces, if you want to check it is continuous, there are several equivalent conditions. So first condition is that the function should be bounded on some closed wall around origin. So either we check the first condition, or we check the function is continuous at zero, or we check the function is uniformly continuous. All these conditions are equivalent to the condition of continuity of the function on the whole domain. And mostly we will be using this last condition. So whenever we are given a linear function f, we will try to find a positive number alpha such that norm of fx is less than equals to alpha times norm x for all x in x. So mostly now onward, whenever we need to check the continuity, we will use this criteria. So this criteria is known as the linear function is bounded, right? So to check the linear function is bounded, that is exactly this condition. So f is continuous, linear function is continuous if and only if it is bounded, right? So these are important criteria which we are understanding from this theorem. So that we define that what is the definition of a bounded linear function? So function is bounded linear if there exists a positive number alpha for every x which satisfies this property. And just we define the notation for all bounded linear function, and similarly we have the notation for all continuous linear functions. So throughout this course we are going to study the continuous function which are mostly linear functions. So now we want to study the characterization of continuous linear map in terms of quotient map. So whenever we have a linear map, let x x and y be non-linear spaces, and f from x to y be a linear function. So we know that whenever we have a linear function, given linear function, we can always associate a subspace of x, which is the zero set of the function or the kernel of the function, because the function is linear map, right? So zero set is basically the kernel, and whenever the kernel is closed, we can define the induced map. So every f will give us f tilde from the quotient space to y, which is defined by f tilde of x plus zf. So this is the quotient space. On the element of the quotient space, we are defining f tilde as the value of fx. So whatever x we are taking, corresponding value fx, we are taking as a value of the function f tilde for every x, right? So now for every f we get a kernel, and for every kernel we get the quotient space, and over the quotient space we can define f tilde function. Now we did not prove this result, we need to prove this result. So the statement of the result is that whenever we have the function f from x to y be linear map, f is continuous if and only if the kernel is closed, and the function f tilde, which we defined just now, is a continuous function. Right, so Vaibhav, we did not prove this result. We are going to prove in this lecture.
Okay, sir. Okay, sir.
Okay, so we want to prove this result, and to prove this result, we have two parts: the implies part and the converse part. So we have defined the kernel here, and we noted that whenever the kernel is closed, we can define f tilde map. So therefore, in the second part, we have f tilde map because we are assuming the kernel is closed, right? So let us start the forward direction of the theorem. So what is the assumption? Assumption is f is continuous function, continuous and linear function, right? So linearity is always there in all these theorems, right? So we are starting with if f is continuous, so what are the property of continuous function we know? What is the definition of continuous function in topology? Do you remember? Over a
Definition of
topological space.
y is said to be continuous if every open set in y is open set in x.
It is called inverse image of open set is open. So basically, if we take the inverse, the sub f is a function from x to y, then if you take any open set u in y, then f inverse u is open in the domain in x, right? So if f is continuous, basically it says that inverse image of open set is open, right? Now what can we say about inverse image of closed set if f is continuous? So we know that inverse image of open set is open if f is continuous. That is the definition of continuous function. But what about the inverse image of closed set? Whether it is closed or not. So these things are related to yeah. So basically, what we are saying is we have a function.
Yeah, sir,
from,
for closed it will be also closed.
yeah, it is closed. So do you remember the proof? What is the idea? So basically, if we take any closed set, let us say A is a closed set, then what will be F inverse of A? F inverse of A is basically F inverse of X minus A complement. And then this is nothing but F inverse of X minus F inverse of X minus A. F inverse of X is the, yeah, so I should take complement in Y because A is a subset of Y. Right? And then F is a function from X to Y. So F inverse Y must be X. And A is closed, so this set is open, right? So since F is continuous, this is open because inverse image of open set is open, and then its complement is closed, right? So this is a simple proof that we study in topology also. You must have seen this in matrix spaces also, continuous function between matrix spaces. So if F is continuous, then inverse image of every closed set is closed. So that means what is the inverse image of 0? That is the kernel, right? So if F is continuous, then inverse image of each closed subset of Y is closed in X under the function F, right? So inverse image of every closed set is closed. So therefore, F inverse of the closed set 0 is closed in X, right? F is a function from X to Y. So F inverse 0 is closed set in X. And what is F inverse 0? F inverse 0 is the set of all X such that Fx equals to 0. So this is basically the kernel of F. Right. So what we have mentioned is that therefore kernel of F is closed subset of X. So in fact you can prove this using sequences also. So whenever xn converges to you take a sequence xn such that f of xn is 0, we can prove that fx is also 0. Xn converges to x. Right. So kernel is a closed set. Now because f is continuous, so xn whenever xn converges to x, fxn converges to fx. So kernel is closed now because f is continuous. So this part we have proved, and then we know that whenever the kernel is closed, we can define this map f tilde, right? So since it is closed, therefore we can define the map f tilde from x quotient kernel of f to y by, what is the definition? F tilde on any element of the quotient space, it is defined as f of x. Right. So this is the definition of f tilde function. Now what next we want to prove? We want to prove that f tilde is continuous function. So if you remember, we discussed some equivalent condition of convergence in the in the quotient space. So I don't know in which lecture number I discussed that. So let me just check. So we discussed that whenever xn plus m converges to x plus m, if and only if there exists a sequence yn, so that xn plus yn converges to x plus y. Exactly which lecture number? Yeah, so here we use that result. Yes, before this. Yeah, so we discussed this result, right? So this result says that whenever we have a y is a closed subset of x, right? If you remember, we have defined this quotient norm whenever y is a closed subspace. So here also kernel is a closed subset, right? That is what we are using here. Kernel is a closed subset. So that means we can define this quotient norm, and then we know that whenever a sequence xn plus yn converges to x plus y in the quotient space, so here y we are taking as a kernel of f, right? That is the closed subset. So that means xn plus zf converges to x plus zf in x quotient zf if and only if there exists a sequence yn in kernel of f such that this converges to this one. So let us rewrite this result somewhere here. So in an earlier result, we proved that the sequence, if we have any sequence in the quotient space, right, in the quotient space, so that is of the form xn plus zf is a sequence which converges to x plus zf in the quotient space, x quotient kernel of f, when only if there exists a sequence yn in the subspace. There exists yn in the subspace such that xn plus yn sequence is converges to x, right? That is the criteria. So this sequence converges to x in x. So in x means in the norm of x it converges, right? And so we are going to use this result now to prove the continuity of the map f tilde. So to prove f tilde is continuous, what we need to prove? Can anyone say that in terms of convergence of sequence? We know the criteria of the convergence, criteria of the continuity in terms of convergence of the sequence. So if you want to show f tilde is continuous, what we need to show, whenever some sequence in the quotient space converges to some element, then f tilde of the sequence converges to f of that element, right? So let us start with that. So this result let us call it some star or something. We are going to use that. So to prove f tilde is continuous, we shall show that whenever xn plus zf, that means we have the sequence in the quotient space converges to x plus zf, right? So this is a sequence which converges in the quotient space, implies whenever we apply f tilde on this sequence, this converges to f tilde of this element. All right, but this criteria, we know what is the definition of f tilde. So f tilde of x plus zf is fx, right? F applied on the first element. If we apply this criteria, then what we need to prove? We need to prove this condition, that is f tilde of fxn plus zf is nothing but f of xn by the definition of f tilde. This converges to f of x, that is this element, right? So what we need to prove? We need to prove that whenever xn plus zf converges to x plus zf, fxn converges to fx, right? If we can show that, then f tilde will be continuous function, right? So yeah, so how to prove this? So again, we know that whenever we have a sequence in the quotient space, we get a sequence yn, right? So now, since xn plus zf converges to x plus zf using the property or proposition star, we get a sequence yn in the subspace. So subspace is the kernel, such that xn plus yn sequence, this sequence converges to x, right? So this sequence converges to x. So now what is, we know here, we know that yn belongs to kernel of f. So yn belongs to kernel of f, that means when we apply the function it becomes 0, right? So what we need to prove? We need to prove f of xn converges to fx. Now if we apply directly the function f both the side, then what we get is what we need, what we have in the hypothesis. So hypothesis says that f is continuous, so that we can use here. So we have a sequence of elements of x which converges to x, and f is continuous, so f of this sequence converges to f of x. This f is continuous, and xn plus yn converges to x. Using continuity, we get f of xn plus yn converges to fx, right? But we know that yn are elements of the kernel of f, right? But yn belongs to kernel of f. So what we get f of yn is 0, right? So if f of yn is 0, then what we get, f of xn plus yn, f is a linear function. So this is essence f of xn plus yn, f is a linear function, so that is f of xn plus f of yn, and f of yn is 0. So that means it is essentially f of xn, right? So f of this sequence converges to fx, that means f of xn converges to fx, right? Because we have f of xn plus yn converges to fx, and yn are elements of the kernel, so f of xn plus yn is essentially the sequence f of xn, and now we have fxn converges to fx. That is what we actually wanted to prove, f of xn converges to fx, right? So that is essentially f tilde is continuous. That is f tilde is continuous. So we proved one part of the theorem, that whenever f is continuous, the kernel is closed and f tilde is continuous. Now converse part. So conversely, what is given? Given that kernel of f is closed and f tilde is continuous. This is given, and what we want to prove in the converse, we need to prove that f is continuous. Right, so to prove f is continuous, what we need to show? So we need to show whenever xn converges to x, f is continuous, we need to show fxn converges to fx, right? So this we need to show. But what we know is that we know f tilde is continuous, right? So now if we start with this condition xn converges to x, right? This we want to prove. So if we start with the xn converges to x, then we know that again by this result, what is given? Whenever xn is a sequence which converges to x, we will have, so this norm is greater than equals to the single norm. So did we mention it somewhere? This property basically. Okay, so let me mention here. Note that whenever xn converges to x, that means norm of xn minus x goes to 0 as n tends to infinity. Right? This is the norm in x. Now, what is the norm in the quotient space? So if we take xn plus kernel of f minus x plus kernel of f. So this is basically the norm of xn minus x plus kernel of f, right? Because it is a quotient space, so we have a vector space addition in the quotient space. So xn plus zf minus x plus zf is basically xn minus x plus zf. This is a vector space operation on the quotient space. And then now this quotient norm, by definition, it is infimum of norm of xn minus x minus y. Y belongs to the subspace, right? And the subspace will always have a zero element, right? So this is over all y, and zero element is always in the kernel. So that means this quantity is less than or equals to this infimum, so it is less than or equals to all elements, and in particular we have y equals to 0. So that means this is less than or equals to norm of xn minus x, right? So now whenever xn minus x converges to 0, xn plus zf converges to x plus zf, right? So this is the result which we are going to use every time, and that is true in fact for all the subspace M, right? Because the norm of y is less than equals to norm y for every element y in capital Y. So that property we are using here. So using this, what we get, therefore xn minus x converges to 0 implies xn plus kernel minus x plus kernel in the quotient space, it converges to 0. What does this say? This says that whenever we have a sequence xn in x which converges to some element of x, then the corresponding sequence in the quotient space converges to corresponding sequence of the quotient space. Right. So xn converges to x implies xn plus kernel converges to x plus kernel. So this gives xn plus kernel converges to x plus kernel. And then we know that what is our hypothesis? F tilde is continuous. So whenever we have a sequence which converges in the quotient space, F tilde of that sequence converges. So this implies F tilde of xn plus kernel converges to F tilde of x plus kernel. Right. So this is a convergence in quotient space, x quotient kernel of F. Right. Xn plus this converges because F tilde is continuous. And yeah, so now what is this? So this is exactly what is F tilde of xn. So by the definition of the quotient map, F tilde of x plus zf is fx, right? So here F tilde of this is basically f of xn, which converges to f of x. So this is what we actually wanted to prove. That was our starting point. We started with xn converges to x. We wanted to prove f is continuous. That means if xn converges to fx. Right. So using xn converges to x, we proved that xn plus kernel converges to x plus kernel, and then f tilde is continuous. So f tilde of that sequence converges to f tilde of x plus kernel, and that is nothing but fxn converges to fx. So f is continuous. So this is one of the criteria, equivalent criteria of continuity. So whenever f is continuous, we can use this equivalent condition. Right. So earlier we discussed 5 equivalent conditions. Right. So where is the statement? Yeah, we ready. So these are the 5 equivalent conditions. One of them is f is continuous, and this one is the sixth equivalent condition, that if f is continuous if and only if the kernel is closed and the corresponding map f tilde is continuous. Right. So now again, with respect to this theorem, if you recall, we proved one result that if we have a linear function its domain is finite dimensional, it is always continuous. It is a linear map. Right. And then we discuss one example when the domain is infinite dimensional C00, there is a function which is not continuous. But we did not use this theorem at that time. This result we proved after that example. So let us see some examples where we can actually apply this last condition in terms of alpha. So we'll see some example which are in fact discontinuous functions. So obviously the domain is infinite dimensional. Because we take the domain is finite dimensional, it is linear, then always continuous. So first example which we want to continue, we want the example of a linear function which is discontinuous. Discontinuous or basically not continuous function. So we are considering this function is known as a differential operator. So let x be the set of C1AB. So what is this set? Can you explain? C1 close interval 0, 1.
That is a set of all continuous and differentiable function over 0, 1.
Yeah, so continuous where and differentiable where? It is continuous on the closed interval 0 to 1 and differentiable over the open interval 0 to 1. Right, and it is one time differentiable function. So obviously 2 times differentiable function will also be there. Yeah, because 2 times differentiable functions are 1 time differentiable. And there will be some functions which are 1 time differentiable, not 2 time differentiable. Those functions will also be there. So X, is it clear that it is a vector space? Operations are pointwise addition and pointwise scalar multiplication. If we take two functions which are differentiable, which are element of these, and we add them, then that function is also continuous on closed interval 0, 1 and 1 time differentiable, right? Because f plus g dash is f dash plus g dash. Similarly, the other property of the derivative we can use, that alpha times f dash is alpha f dash. So using those properties, we can easily see that this is a vector space with respect to pointwise addition and scalar multiplication. So X is a vector space, and the norm we need to define because we want to take the non-linear space. So let X be this with supremum norm. So you remember supremum norm, right? What is the supremum norm? Supremum of modulus fx. So many students do mistakes here, they take fx. So remember that norm is always non-negative. So we need to take modulus here. Like in the other norms, we are taking modulus of the coordinates. Right. So this is a norm over this vector space. We can check it easily. And yeah, we already checked that this is a norm on C01, but it is also norm on C101. And with respect to this norm, if we consider the codomain, so that is Y is a set of C01 with the same norm, supremum norm. Right. So the same norm we are defining over domain and codomain, and we are defining the function. So let f from x to y be defined by f of x is equals to x dash. What is x dash? X dash is the derivative of x. So if you have a function x in C101, if you differentiate it one times, then it will give us a function which is continuous. Right? The derivative may not be differentiable, but because we are taking the function is C101, the derivative is always continuous. So yeah, it is clear that this is a, because this is a vector space, f is linear. Right? We can easily check because f of x plus y is x plus y dash, and that is nothing but x dash plus y dash. So that is f of x plus f of y. Right. Similarly, we can check the other property. So the scalar multiplication. So therefore, f is a linear map. Okay. So now, what are the simple examples of the function which are differentiable?
All the polynomial functions.
Polynomial, sin x, cos x, and all that. Right. So the simplest polynomials are powers polynomials, right? So x square, x power n, and so on. So here we are using notation x for the functions. So we will consider the function is a variable of t, right? So note that x and t, right? So x we are considering as a continuous function. So these are the continuous function defined by t power n. All these function belongs to x. So all these functions are one times differentiable, and the derivative is also continuous on closed interval 0 1, right? So where n is a natural number. So now we have a sequence of functions which belongs to x, right? X is the C101, and what is supremum now of xn?
That will be 1.
That will be 1, right? So all these are the unit vectors. So what we want to prove here, if we apply this theorem, we need to show that we need some alpha such that norm of f x is less than or equal to alpha times norm x for every x. In particularly, this condition will hold for the unit vector also, right? So if you take unit vector, this is 1. So that means fx should be bounded by some fixed alpha, some fixed positive number alpha, right? So if we can find the alpha, then f is continuous, right? So if we can show there cannot be any alpha, so that norm of fx is less than equals to that number. So basically, if norm of fx is unbounded, right, in some sense, then f is discontinuous. So let us see here what is happening. So note that norm of xn is 1. So suppose there exists alpha greater than 0, so norm of fx is less than equal to alpha times norm x for every x in x. Suppose this is true. And now what are the norms we are taking? We are taking supremum norm, right? In the domain and codomain both. So we are assuming the function is continuous. So if it is continuous, there exists some alpha which satisfies for all x. So in particular, this condition is satisfied for each xn also, right? Because xn has norm 1. In particular, if you substitute xn in this equation, then what we get is norm of fxn, subnorm of fxn should be less than equals to alpha, right? Why? Because norm of xn is 1. This is 1. So other thing we already mentioned, right? So if f is continuous, it should satisfy this condition for some fixed alpha, fixed positive number. Now we'll find what is subnorm of fxn, right? So now note that what is fxn? So fxn means we have defined the map. Fx is derivative of x, right? So if you take xn is this polynomial, then what will be the derivative of this polynomial? Derivative of x power n is n x power n minus 1. So here the variable is t. So that means derivative of t power n is n times t power n minus 1. Right. So derivative is n t power n minus 1. So now we know fxn, so we can find its supremum norm. So therefore sup norm of fxn is basically supremum of the domain of the function is 0, close 0, 1, and we need to take modulus value of the function fxn. So that is n t power n minus 1. Right. So, so basically, yeah. So if you want, we can write one more step. This is fxn, and that is supremum of n times t power n minus 1. Right. So now n does not depend on t. So we can take n outside because n is a natural number. So it will come outside supremum. So what is supremum of this number? If t is between 0 and 1. What is supremum?
Yeah, 1 again.
That is 1 again, right? So if you want, you can take two cases, n is 1 and n is not 1. N is 1, then again t power 0 is 1. So in that case also you will get 1. So that is essentially n. So this supremum is n. So now can we have a natural number n here which is less than equals to alpha for every natural number n? So is it true? So can we have number fixed number alpha so that every natural number is less than equals to that fixed positive number? That is not true, right? Because otherwise set of natural number will be bounded above. That is a contradiction. So this contradiction is arising because of the assumption that there exists alpha. So that means there does not exist alpha satisfying this property, right? So that means the fifth condition fails, and fifth condition fails. That means f is not continuous. Which is a contradiction. Therefore, such alpha greater than 0 does not exist. So basically what we are saying is f is not bounded linear function. So it is not bounded linear function, that is same as f is not a continuous linear function. So f is linear but it is not continuous because the fifth condition fails, and that is equivalent to this third condition. So it is not continuous. Okay, so this is first example of the linear function, which is a differential operator. It has some application in differential equation, and which is not continuous function. It is linear, but it is not a continuous function. So we'll see some examples later on. One example, we already know that whenever domain is finite dimensional, all linear functions are continuous. We'll see some examples when the domain is not finite dimensional, but still the function is linear and continuous. But as of now, we need some examples which are discontinuous function that we'll be using several times as a counter example later on. Okay, so I think this is enough for today.